I'm David Upslade. I'm a senior GS consultant at Mark McDonald. And today, this long title, I'm going to be talking about advancing noise modelling with data science and FME-enabled automations. So I've worked in with GIS for the last 10 years. I actually started my life as a geologist. And sort of geospatial data sets and things that involve a lot of map data has basically been at the forefront of what I've been working on for the last 10 years. And this project I'll be talking about today is definitely no exception to that. Whilst also being one of the most complex things I've worked on as well. So just a quick introduction to who Mark McDonald are, for those not familiar. We're a global engineering, development and management consultancy. Also one of the largest wholly employee-owned organisations of its kind. We plan, deliver and maintain transport, energy, water, building and wider infrastructure that's integral to all our daily lives. And the focus of what I'm going to be talking on today is environmental noise and how we've been modelling that. And specifically noise pollution. So noise pollution affects millions of people across the world every day. Contributes to hearing loss, high blood pressure and sleep problems. The first stage really in targeting these problems is easy, accurate data on noise sources, but also the geographical influence of those noise sources and where that noise is felt. So noise hotspots, but also the impacted groups, and that can help us further identify actions to mitigate against those. So these health problems, what I mentioned before, especially affect young people who can suffer from stress, anxiety, memory-sensitive problems, and noise pollution is also believed to lead to increased risk of developing dementia later in life. So it's kind of obvious from that last slide, but why is action needed? Well, the World Health Organization has registered over. It states that noise pollution is the second biggest cause of environmental ill health in Europe. Environmental cause of ill health in Europe, I should say. And the Chartered Institute of Environmental Health annual noise survey logs over 365,000 noise complaints in 144 local authorities just in 1 year alone. The annual cost of noise is £7 to £10 billion, and just the noise complaints themselves, the cost of those is 73 million. So Defra is the organisation that's responsible for dealing with those noise complaints. It has cross-government oversight on environmental noise policy in England in line with the government's aim to promote good health and good quality of life through effective management of noise. So what was the vision then of this new noise modelling system that we worked with Defra on? So the principles of delivering strategic noise has been defined for several years. There's been noise maps generated on a yearly basis for some time. But Defra's vision was to transform this noise modelling and provide data-driven evidence and to create a new detailed noise model and a whole system to generate that. And it would be done using the latest sort of industry standard technique, which is referred to as EU Knossos modelling system. So the previous manual methods of modelling noise were very slow, expensive. They offered limited coverage, but didn't offer the whole. They didn't necessarily cover all those in all areas of the UK in detail. And all that manual work that went into generating these maps led to a one-off result, basically, which, in order to refresh or create again with the latest currency, meant doing that process entirely from scratch. We can see some examples of the noise maps, noise models that we generated at the top there. So Defra's vision for the news modelling system was to resolve these issues using FME-powered data. Talk about FME quite a bit in this presentation, in a way that's never been combined before. And they really wanted, as part of that vision, to be able to own the model itself. So we developed open data standards for all components of that data set, and that meant that for all these aspects of the noise modelling system, they could be easily used in other GIS or other noise calculation packages beyond the system itself. the aim was to have full coverage this time across England, so not just agglomerations and not just the major roads, but all roads and all railway lines across the whole of the country, modelling noise generated by all of those. But also not just the noise model, as you can see at the top there, that we wanted to be able to use and sort of generate, but also all the underlying data that contributes to those noise maps, the roads themselves, the 3D environment, the buildings, the landscape. And then also, because by having that information, we'd be able to do scenario modelling. So what happens, for example, if we have new roads, what if there's more traffic on those roads, what happens to the noise level in different areas? We'd be able to model all those things by having all that information available to us, and to have our client have that information as well. But taking that one step further, not only what happens to the noise level, but who is affected, we've also integrated population data into the data sets this time. So we can see, as noise levels change, who is affected, how many people, where are those people. So these are all the sort of vision that Defra had for the new system. Change slide. So really, the ambition of Defra, compared to whatever I meant, but it's a really quite significant innovation with this product, and it's quite a step change in how noise modelling is done. We work with our partners, Noise Consultant Limited, who is noise modelling consultant in Manchester, to do a lot of this work, and we've won quite a lot of awards throughout the last 4 years as products have been undertaken. So the objectives, really, of this new system, like I mentioned before, it's national scale, but at localised detail. So it's all road and all rail, which means that information and calculations and findings could be done from a local authority level across the whole country. Another objective was to be able to ingest from a really wide range of different data sources from all sorts of vendors, which we'll come on to talk about, and with that data to automate how that was used, the integration of that data to produce the various intermediate data sets, and the end noise map itself had to be done in an automated way with no manual intervention, so that it would be consistent and also time efficient. All the different data sets involved in this, and the noise map itself, we generated to open data standards that we defined and have made accessible to the end users, so that they can then utilise the data and they can understand the inputs and outputs of the whole process. And we've stored this data in a way that's accessible to be able to do that analysis in a really structured database system. But also, the end result, the noise map itself, is available at number 6 there, and on a cloud-based platform on the web, where users can actually access it through a user portal via a service, a web service, but also via a series of tools, which I'll come to talk about, where the true value of those maps can be sort of gleaned in another way. And the noise consultants in Manchester, the actual modelling of the noise itself was carried out using these latest techniques of CRTN and Kenosis, the industry standard noise modelling techniques. So noise modelling system, you heard me say that word a few times now. What does it look like? So the noise modelling system is designed as a web accessible cloud computing service that connects a series of components. And the component that I'll be focusing on for the remainder of this presentation is really the data engine at its core. So this is the main part that brings in all the data from all the different data sources, automates it, analyses it, transforms it, and outputs it into a series of data sets, but ultimately the noise map itself. And in a cost-effective manner, and it's used at its heart with software, which some of you may be familiar with, some of you may not be, but it's from Safe Software, it's an FME, and it's a server-based application called Flow. So these tools can be run directly from the web. The user would upload their data sets that we've run through a user interface there, and the outputs were generated and it made it accessible to them. So on this slide, we talk about the data engine that we developed at McDonald's. And it's twofold, or two sort of aspects to it really, that we were working on. there is the environment, the 3D model on which the noise would be received, which we call the 3D propagation model. That's the ground cover, all the buildings, the roads, embankments, everything really on the surface. And then on the next slide, we'll talk about the sound source model, which is where the sound is coming from. So you've got the two parts really. This is where the sound is coming from. This is how much sound there is. This is the surface over which that sound is felt. And then the consultants and the managers were the ones who modelled, made the map that connected those two pieces together. But this one, on this slide, this is the propagation model. The starting point of the propagation model was surface data. So we had the environment agencies 1 metre DTM model. We also had the Ordnance Survey's 5 metre DTM model. Coverage on the environment agencies map was not complete across all of the UK, and we used, therefore, dynamic interpolation to combine these two surface models together, which led to a generation of our integrated DTM. This DTM, integrated DTM as we refer to it, was sort of the integral starting point for the 3D propagation model, because all the other components I'll come to talk about were draped onto this surface. So we had accurate elevation values, all the nodes across all the different cells on this surface data sets. Starting with contours, which were extracted at 2 metre intervals, and we had spot heights, again, which were extracted at 25 metre intervals this time. And then we had a series of components which we derived from Ordnance Survey's topography layer, starting with break lines. So we took those from the topographic layer and then we draped them onto this integrated DTM. So we had a really accurate height value for this vector data set. We did the same with buildings. We joined building height data set using the UPRN attribute of this data set, which allowed us to extrude these buildings into 3D. Where we didn't have that information, we looked at the differences in the DTM data sets to be able to work out what the heights of those buildings were. All the while making sure that the base of those buildings was draped and integrated with that DTM that I mentioned before. Bridge decks are one of the most challenging parts of this particular model. We needed to make sure that the bridges and the bridge decks crossed at complex junctions, like you see on the screen here, but they actually crossed at the right level, but they weren't just stuck on top of each other at one Z value where they met, where there was that correct separation. Getting that aspect right and getting the 3D environment correct is integral to understanding where the sound will be received or where the sound will be blocked. So it's important that we got that 3D property of all the bridges in the UK, we got that correct. And this goes back to automation is key, because we wouldn't have been able to do that manually for every bridge in the UK. Break lines, sound barriers, alongside those, getting those propagated correctly in 3D. A key component, because they're going to block sound from the sound sources to where the sound will be received in buildings, for example. And road centre lines, so I'll talk a bit about that. That's one of the main things that I've been working on myself in this whole project. These came from the Ordnance Survey's highway network roading data set. But they also were draped onto this integrated DTM, but they also define the source from which the noise would then be felt across all the different propagation models. You'll notice orange things appear on the buildings. These are the facade points, so we're not just considering buildings, just the building alone. We care about the different aspects of that building. So sound might be more prominent on the north from that, coming from the motorway than it would from that slip road to the south, for example. So understanding that, what dwellings and how many people are in those buildings lets us model the sound and who's affected even more accurately. And the final part of this propagation model was to integrate average temperature. We had meteorological data station points that we integrated onto each of the interpolated across all the different road lengths in the UK to be able to work out what the temperature would be at that road surface. So that's the propagation model. Now a sound source model. Again, the starting point, as I mentioned before, is the Ordnance Survey Highway and Oak 3D road sensor lines. It had been draped by this stage onto our digital, integrated DTM. The Ordnance Survey dataset comes with some attributes that helps us understand the importance of roads, so the road category, whether it's a motorway or minor road, Jules Carter, for example. But to calculate noise emissions, to estimate what they are, a lot more attributes are required than that. We need to know about traffic flow, we need to know about speed, we need to know about road surface. Another 60, more than 60 attributes were therefore attributes onto these centerline datasets to be able to then lead to the calculation of noise. Starting with whether it's a major road or not. So here we have the blue roads, the major roads. They're roads with more than 3 million vehicles travelling across them per year, and all the grey ones have less than that. In order to get to that value, we need no traffic flow. And we'll come on to that in a few slides' time as well. This is showing gradient, with green roads being flat and yellow being a steep or low gradient, or positive and negative gradient. And in fact, the draping this data on the integrated DTM was integral to be able to do that on an accurate and more regular basis. This one is showing distance from junction. So why do we care about that? Because we care about where vehicles are accelerating or deaccelerating towards and away from traffic island junctions and roundabout junctions, because the noise generated in those activities is different to a vehicle travelling just normally along the road. So all these different aspects are integral to understanding and estimating how the noise will vary, really. And this was quite a challenging process too, to be able to understand where the main traffic flow will be coming away from a junction and stopping it from going down minor roads, for example, was a key part. This is our traffic flow. So each of these bubbles is showing a count of vehicles, and that's for every road in the UK. The sources of that data were National Highways WebTrees dataset. We pulled that using what's called the best API connection, so it meant we actually had a live feed to the data in the tools itself. So for each tile data, we were pulling it down, so a live currency data. We also had Department for Transport's traffic count dataset as well. That didn't cover, those observed values don't cover all the roads in the UK, as you can probably imagine, which meant that we also had a gap filling process we had to do. So we had a series of 23 rules, which included things like interpolation and extrapolation and splitting at different types of junctions, which allowed us to filter all those traffic values from the observed values onto all legal roads in the UK. Speed data as well, so average speed data for those roads was appended to those road centre lines. That came from, again, WebTrees, and it came from the Ordnance Survey's average speed data set. So the final part of the sound source process was to then calculate the noise emission from all those attributes. There's a complex script that then worked out for numerous different categories, of vehicular categories and for time-based categories, and using different modelling systems, whether that be Knossos or CRTN, what the different levels of sound in decimal values would be felt on each of those road links. These are just nice little images sort of linking the two together. We've got the 3D propagated, the extruded buildings, the ground cover. We've got this road centre line in yellow to make it its way through. So you can see the road sound source and all environment from which that sound from the source would be received, which put together and with our consultants down in Manchester could lead to the generation of this noise map model itself. And this is just another view of the sort of the bridge scenario we had. You can see what the satellite images said the bridges are doing, sort of dropping down. We couldn't allow it to do that. We had to get the bridge stack at the right level, so to cut across from one embankment to the other. That was, again, it was quite a complex challenge to get that to work, especially sometimes when we had 2 or 3 bridge stacks on top of each other. So we looked at what we'd done with the data and what we were aiming to build. And that was one of the objectives of the whole noise modelling system, was to generate the noise model, the latest currency of the noise model. But one of the objectives was to actually have the tools that make the system available so that they could be used again to generate new noise maps. So we didn't have the same issue as we had in previous years of having to repeat the whole process. We could have the tools in place and you could put new data in and you could generate maps again. So with that in mind, we generated a series of web. We put all the tools that we use to generate these different components onto the web. We had 15 tools for the propagation model, which dealt with all the different aspects like bridges and breaklines and ground power per tool, and gradually we used to build up that propagation model. And likewise, I had 15 tools for the sound source. Again, we dealt with things like traffic flow and resource data and gradient, all the separate tools. And the user could go onto the web and upload their data and use our data and generate those outputs, those intermediate outputs, but then would lead to a final sound source model or final propagation model. What we also generated on the next slide, so those two sets of tools were about generating the noise model and getting to that stage of saying this is where the sound is. But when we did that, when we had those tools published and we had the actual noise map there online, the next stage was then to say, right, we went to our stakeholders and went to all the potential end users like Network Rail and National Highways. We had a period of consultation and questionnaires with them and said, what do you want to, what would you use it for? What are your main problems that you'd like to solve? And that led to a series of further end user tools, which kind of augment the findings from that noise map. So one of the first ones, the obvious ones, was to be able to allow them to basically get access to that underlying data. So they could see the noise map on the web map service, but they wanted to be able to say, well, I'd like to be able to download all the buildings that generated this map from this particular area. I'd like to get all the bridges, all the rail centre lines. So we made that data available to them from the model data download tool. The next thing the user might want to be able to do is to be able to summarise noise level in a particular area. So not just to have to query the map and say, oh, it looks bad or it looks good, but to have a sort of standardised statistical report stating the noise level in an area of interest to them. So they could draw an area of interest, say in the centre of Nottingham, and it would analyse all the different results in that noise map and say that the average band value is maybe 55 decimals. That's what I've just made up for the purpose of this talk. But then they might come over here in the middle of rural area around Keyworth and actually find that the band value is on average for the same area of land much lower, say 40. So getting that quick tabulated findings from an area of interest to them was the nature of that tool. They also might be interested in understanding how the noise variations correlated with their own information and their own statistics. They could use the joint statistics tool that we created for them to add, say, health data, which had a spatial component, and look at the correlation between health and the noise bands. And the final thing, which I mentioned on this slide, but they said they wanted to do was to understand why is it noisy. So if they had a noise hotspot in a particular building in a particular area of town, if it was really noisy, they wanted to say, well, what are the sources of that noise? So this tool, they could pinpoint a building, they could pinpoint a location, and it would generate as a geospatial format, as geodata sets, and also as a map the actual roads and rails that were contributing to that noise. It might not be the nearest road, as you might think. It might be the motorway that's 500 metres away, because it's obviously that much noisier. And that, obviously, for local authorities is really important for them to be able to understand what's the target. If you want to tackle noise issues, where do we need to target be?
2 minutes, maybe.
2 minutes. This is just showing how one would access these tools online, but I'll not go through the whole thing because it's more than 2 minutes, I think. So on the final slide, it's just sort of some comments on the process we went through to generate those self-service and end user tools. And it's all not really kind of a learning curve, but in terms of getting the best offering for our end users, we have to think about various aspects. So the user experience, making those tools sort of intuitive to both technical and non-technical people, but also making the tools provide feedback if they weren't being used in a certain way. We knew how to use them because we developed them, but it was if the wrong inputs were put into those tools, we had to have error handling. There's really quite a broad error handling process in the end, but checked all the aspects of what the user would put in there. Functionality goes back to the previous slide, really, so making sure that the tools themselves are really generating what the user wanted, what they could get the most out of it, but also making sure that the tools performed as optimally as possible. I mentioned in the previous slide that one of the outputs, for example, would be Excel spreadsheet summarising how much noise it was. Well, actually, the input to that might be 50 or 70 million rows of data that had to be queried from the database, all to produce this Excel. So the performance has to be optimised of these tools to be able to do that. We wanted it to be secure. We used security such as markup language protocols in place to make sure that these tools were as secure as possible. And we wanted to make them accessible to end users. So we're generating APIs that allows users to be able to integrate these tools with our applications. And we're basically maintaining them as where necessary, keeping user guides and documentation up to date. And we did an extensive amount of testing, and now that the tools are in place, we're analysing, and they're live in fact with the test group, we're analysing how they're being used and really which sort of use cases are most popular with those. So it's a kind of an evolving process where for the next round we can better enhance them. So I'd just like to thank you for listening and finish on a nice little view there of the noise map. So yes, thank you.